There's this one here. Here we go. All right. Welcome, everyone. My name is Dallon Penney. I'm a PhD student at the University of California, Santa Barbara. It's my email, QR code to my LinkedIn page if you want to learn a little bit more about me and my background. But a brief rundown, I'm a second year in the Barado lab, so it's a physical chemistry lab in the chemistry department. And I'm studying vanadium redox flow batteries, and I thought I'd share some of my research into these systems with you all, and hopefully you'll gain a better understanding of why I think it's the solution to the energy storage problem in renewable energy. A little bit more about me. I grew up in Fresno, California. I've lived over mostly western United States. I haven't been further east than Texas. Most recently, I came from a job at Freeport-McMoRan, which is a copper mining company out in Arizona. So moving on. So the renewable energy problem, this right here is called the duck curve. You can kind of see the vague shape of a duck here if you really use your imagination. So what this curve shows, this blue curve here, is the load on the grid for Southern California in megawatts. So it fluctuates throughout the day, peaking at around 8 p.m. And this curve is the amount of power produced from solar and wind in Southern California. So as you can see, this peaks around 4 or 5 p.m. Or around the middle of the day, and then it goes down right as the demand starts to increase. So this is due to the sun setting and rising, obviously. So diurnal fluctuations. You can't produce power at night with PV photovoltaic systems, and wind also is very weather and day-night dependent as well. So we have this compounding problem of demand not matching up with production. So we need a way to smooth this out and make it so we can have this be a nice matching line that matches the demand from our system. And this also kind of mirrors what happens in a house in terms of how much power is used throughout the day. So energy storage is one solution. It's kind of the best solution that we have to overcome this problem. Production and demand discrepancies can be smoothed over by storing the excess power that you create during the day to be used later during peak demand. So that's called peak shaving or load leveling. Batteries are kind of the best solution for that. They're the most mature technology. They've been around for the longest. They are also modular and very efficient. This obviously is just a lead cell battery. I'll be talking more about the different types here. So, what's available right now? This is a graph that I created mostly lithium iron phosphate and nickel cobalt manganese lithium ion batteries that are available on the market right now for residential PV battery systems. So this axis is the amount of warranted kilowatt hours per system. So basically how many units of power you have over the warranty versus the price. So as you can see, as these increase, the price generally increases, and then the power of each system is the size of these dots. So this was all taken from solarquotes.com. It's just a big open source database that they have online. And like I said, this is mostly lithium ion, and so at the upper end you can get upwards of $25,000 for a single system. That's kind of a ridiculous amount. That's the amount of a new car or sometimes even an entire solar system itself. So the price is a huge factor in the consideration for battery storage. How do we make it cheaper? How do we solve this problem without completely bankrupting our without making completely economically unfeasible? So a better way would be to use a better system, and here I present the vanadium redox flow battery. So a flow battery is a kind of battery that uses liquid electrolyte. So we have, so we have here two tanks that are connected to a cell where the actual chemistry takes place. It was first this kind of flow battery, the vanadium flow battery, was first successfully demonstrated in the University of New South Wales in the 1980s by Skyles et al. And her group, or his group. And so pumps are needed to move this electrolyte from these holding tanks to the reaction cell. And this is a repeating unit, so you can stack these on top of each other, with each cell being a nominal voltage of about 1.3 volts. And then separating these two half cells, you have an ion exchange membrane where you're conducting hydrogen ions or protons between these two half cells. So in layman's terms, this is basically the whole battery, and you can charge this by running this either forward or in reverse, and you charge it by changing the oxidation states of this metal that's dissolved in an acidic solution. So these are the two equations for each half cell. So on the anode, we are giving electrons to V3 plus to make V2 plus, and at the cathode, this is V5 plus going to V4 plus, and back and forth, discharging and charging. So how does it work? So this is the discharge state of the cell, the battery. So on the cathode side, we have about 1.7 molar, or 1.7 moles per liter of V4 plus in a acidic sulfuric acid matrix. And we have the same concentration of V3 plus on this side. And this is our ion exchange membrane. The industry standard is something called Nafion. It was originally developed for fuel cell applications. This is a drastically different environment than a fuel cell. Therefore, this is a very low power density. So the power per unit area is very much lower than you would have for a fuel cell. But the whole system is a lot more efficient than any fuel cell on the market. So when you want to charge this thing, you end up making it look like this, where you go from V4 to V5, and it changes color from blue to yellow on this side, and then from green to purple on this side, all while pumping these solutions to make sure you're replenishing each species as it gets oxidized or reduced on each side. So vanadium is kind of the central to the architecture of this. It is number 23 on the periodic table. It's a transition element, transition metal. Pretty common in the Earth's crust, about as common as copper. Most of the demand is for ferrovanadium, which is used in metals, specifically steel manufacturing, making hardened steels. And China produces the lion's share of the vanadium in the world, followed by Russia, South Africa, with the United States and Brazil bringing up the lead. So it's not an expensive metal. The price fluctuates quite a bit, but it's about as expensive as copper. So it's not like it's at the same level as platinum or gold or even lithium. So what are the advantages of this battery? It has the highest cycle lifetime of all presently available batteries, including lithium-ion batteries. About 20,000 cycles you can run this thing without ever damaging it. Safe and stable at all levels of charge, and the nail test only causes about a 1 degree centigrade temperature change. The nail test meaning you drive a nail through one of the cell stacks, it doesn't blow up like you would on a lithium-ion battery. Fireproof, on that same note, they're 80% water, so these tanks are dilute acidic solutions. They won't burn, as opposed to a lithium-ion battery. They're completely recyclable. all the vanadium can be recycled and recovered. There's only one electroactive species on both sides of this, so if they mix, it doesn't destroy the battery. It can be discharged completely down to with no damage to the capacity over the cycle lifetime, as opposed to lithium ion, you can only charge it down to about 10%. Anything further than that, you start to damage the battery and you lower its operating lifespan. They're also modular, so the power and capacity are decoupled. So this determines the power is your area of your electrode, and the energy is determined by the volume of your tanks. So you can scale these to whatever size you want, and you can stack these as however high you want, and that determines the voltage, power, and capacity of your battery. So these things are completely modular. These right here are made from recycled chemical totes. So these you can buy online. They come in standard sizes, and they've just been repurposed for this battery. So I can already see some people are starting to use recycled materials to make these batteries. So some disadvantages. It's not all perfect. They have a very low energy density compared to other batteries, only 25 watt hours per liter, compared to some of these other batteries on the market. So they don't stack up next to lead acid, nickel cadmium, nickel metal hydride, lithium ion, or sodium sulfide. So lithium ion has the highest energy density out of these batteries. Also, vanadium oxides are toxic, so that's a risk involved with these kinds. They also have acidic electrolytes, obviously, so you want to have special containment procedures to keep spills to a minimum. And you have to kind of over-engineer them and make sure everything seals really well so you don't have any kind of leaks. They also have a lower round-trip efficiency than lithium ions at about 85%. Lithium ions also kind of have the best in terms of round-trip efficiency at 95%. And this is some of the other efficiencies of these batteries as well. Current research. So most research is focused on improving both the energy density and the power of these cells. So my research specifically is about the membranes used in these cells, and I am developing a way to image these ion exchange membranes while the battery is operating using something called an atomic force microscope. So what an atomic force microscope does is you can get 10 nanometer resolution of a surface, both topography and conductance, all at the same time, with a little metal probe where it was driven out of its oscillating frequency, and you're collecting data off of that using a laser. This is kind of the design of the cell that I'm making to fit inside the microscope itself. This has gone through, this isn't actually the latest one, this is the one I had the nicest picture for. Yeah, so the price and efficiency and power density for these batteries is always increasing, and I mean the price is lowering while the energy density and power for these batteries is increasing. So they are becoming better and better as more research is done on these. So this is another graph to show kind of how these batteries really shine compared to other batteries. So here we have the cycle lifetime of different kinds of batteries against the CAPEX, which is the capital expenditure. And the units that I was given that I was working with was euros per kilowatt hour. So all the way over here, the very end here, we have lithium ion as being the most expensive in terms of capital expenditure per kilowatt hour. And then kind of grouped in down in midway, we have the vanadium redox flow battery, as well as lead acid and nickel metal hydride. And then towards the lower end, we have these zinc air batteries, nickel cadmium, and sodium sulfide batteries. So as you can see, this battery far outperforms all others in terms of lifetime, and it's about, you know, much less the cost of a lithium ion while increasing the lifetime of the battery. So these are the current large-scale projects around the world for these kinds of batteries. Sorry, it's kind of small. I can't really read it, but green is in Europe. So most of these systems are in Europe or Asia, specifically China. China has the largest one in the world. I think it's about 500 megawatt storage capacity. So this kind of ties into what I'd like to do as a startup opportunity. The low capital costs allow for easier startup and production of batteries. It's roughly 12 times less expensive than a lithium-ion battery to produce one of these things. And when you consider all the factors, including cycle lifetime and material costs, partnerships can be made between solar companies for residential applications. There's been a lot of interest recently into designing these things for residential PV systems for someone's house. So it would last basically the life of the house, 20,000 cycles. Is if you cycle that once per day, that's 20,000. That's 20,000 days of lifetime for that battery. And I'm also participating in the new venture competition at UCSB this year, where hopefully I can take this idea and try to build a business around it. So, in conclusion, the vanadium redox flow battery is a strong contender for the most economical battery for grid, microgrid level applications. Ongoing research seeks to improve every level of the battery, including its power density, energy density, and efficiency. And it presents a viable solution to this duck curve problem of storing the energy we make from renewable energy and making it more viable to transition to renewable energy sources. I'd like to thank my PI, Stephen Barato, and Swiss, Michael Bayless, for hosting this, and the whole Hackerspace for helping me prepare this talk. Yeah, any questions? Yeah. Sure.
So I understand that using that vanadium occurs with other metals that are more valuable a lot of times, so it ends up with tailings and mines and stuff. So if that's were to create a demand for vanadium, do you think the United States would be able to increase its production significantly?
Yeah, they have a lot of it just lying around from what I've read, and like I said, most of the demand is for steel production. So the price follows steel production pretty closely right now, at least in the United States. But if there was a new demand for it, I'm sure that there would be a lot more interest in recovering the tailings from other mineral sources. Yes?
So, in that picture where you had the two totes,
Mm-hmm.
those look like each 1,000-liter totes, and you had, said 25 megawatt or watt hours per liter.
Mm-hmm.
So that would be multiplying up about 50 kilowatts, kilowatt hours of energy potential. That unit in the middle there, how much power would that? How many kilowatts?
So it's about 0.5 watts per centimeter squared.
Okay.
So I'd have to run the numbers on that. I'm not sure.
So would that be like a household? Like I was kind of wondering.
That would be bigger than what you need for a house. So you probably half that. You probably only want 15 kilowatts for your house for a solar PV system.
About 12 feet wide.
Oh yeah,
that image, how big was that? I mean, you mentioned 1,000 liters, but that was.
I mean, one of those containers is about
Yeah.
this by this big, so it would fit in your backyard easily.
Or
Yeah.
your garage.
Or your garage, or you could bury it. You could even bury these tanks below ground, and they'd be perfectly safe. Yes.
I'm not familiar with the term round-trip efficiency.
Round-trip efficiency is when you cycle it completely down and then cycle it back. So you completely charge it and then you discharge it. How much energy did you lose in the process? So say you started with 100 joules of energy, and you're left with 85 joules of energy, usable energy by the time the whole thing is done. Yes?
Compared to a lead acid battery, the sulfuric acid, what concentration?
I'm not sure what the concentration is in a lead Does anyone know that?
I'll search.
Okay.
You can buy it on Amazon. So it's not up for that.
If has anyone got it in molarity, I could do a direct comparison. Yeah. In look it up too.
Anode, your cathode, the material is
Carbon. They usually use graphite or carbon felt or some other material like that, so it's not an expensive or catalyst loaded material. Nope. It's just regular old graphite felt.
would 40% by weight be a useful reference for you?
Yeah, it's less than that then. It's a lot less than 40%. Yeah, it's a lot less acidic than a lead acid battery.
Nicer to have around.
Yes, yes.
Listen, so you mentioned like the largest installation is in China,
Mm-hmm.
and how does that one compare size-wise to an existing pumped hydro or other grid scale storage?
Bigger than most, yeah. So this thing is hooked up to a huge wind farm, and it's producing, it's something on the order of like 500 megawatts per, I can't remember if it's hours or I can't remember what the units were on that, but it's basically like a hydroelectric dam size kind of project. Yes.
Are the scaled up batteries scaling up the tanks themselves, or are they duplicating essentially what you had in the photo where you had tanks and then
So the power is based on the area of your electrodes.
right?
So the more power you want, you have to scale that with the area of your electrodes, and the more energy you want to store, you have to scale that with the volume of your tanks.
So they're scaling both of those up to a larger level.
Yes.
What's your target current density for that electrode?
Most people do, for most commercial systems, it's about 0.5 meters for area, total area for electrodes. What's that?
Current density, so amperes per.
Per centimeter squared, I want to say. Yeah.
Does anything degrade over with age? Like output or
So
lithium ion over time?
So the lithium ion, you damage it when you cycle it completely. This one doesn't get damaged. You do if you there's oxides that can form at higher temperatures. So oftentimes they'll add in a stabilizing agent such as hydrochloric acid, which actually the chloride ion stabilizes these oxides that form on the V5, V4 plus side. Really the energy density is limited by the solubility of these ions. So the reason why you can only get to 1.7 molar is because you can only get 1.7 molar to dissolve in this acid on the V4, V5 side. You can get a lot more concentrated on the other side, but it's because of the solubility of these other ions that you're kind of limited by that energy density. Back first, yeah.
In the cell itself, where's the expense in building
The membrane. The membrane is by far the most expensive part. So I mentioned Nafion. Nafion 117 is a DuPont, or no, not a DuPont, some chemical company came up with that, and it's a fluoropolymer backbone ion conductive membrane. So it's basically a Teflon with a sulfonic acid side chain, and it conducts protons really well for fuel cells, but my research is trying to find a better membrane for these applications that, and they also allow vanadium to cross over between it. So it slowly discharges itself if you have that Nafion membrane, but that's the most thermally and mechanically stable one that's on the market right now.
Approximately how much would it cost for a square meter?
Square meter, oof, a couple $1,000. Yeah.
So my question was just, have you built one of these things and how big was it?
So the one I have in the lab has the electrode area is a centimeter diameter, and the electrolyte tanks are about 70 milliliters each. So not very big, but it's a good test bed for what I'm doing.
How much cheaper do the batteries need to be before, I forget, how cheap they say the batteries need to be before we can actually use them widespread?
The biggest thing right now is just like material costs. the whole engineering and things like that. So if we can find a more cheap membrane, I think that would lower the costs, because vanadium prices are subject to, whatever they're subject to, but the main cost that can be driven down for this system is the membrane. So as soon as, well, hopefully I'm collaborating with a group at UMass Amherst that's developing these membranes, and I'm going to be imaging them and seeing how well they operate in operando. So we should be able to get some rapid feasibility tests going here pretty soon. Did that answer your question? Okay.
So the number of cycles, is that, do you find enough upper limit, or is that just?
That's the upper limit, yeah.
And if there wasn't any degradation, what happens when you get to that?
You can recycle them. So
I mean, what causes it to stop working?
the stack itself breaks down. So the membrane kind of gets junked up, and that stops conducting, and then the electrodes start to degrade, and you start to get a little bit of degradation in the electrolytes as well, but not most of the degradation takes place where the reaction's happening.
You get that heat buildup, and are you potentially able to grab that heat?
So it operates best in cooler temperatures because of fluid dynamics. So the pumps are more efficient when the electrolyte is colder. And that's kind of the limiting factor there. But it does operate under pretty much all ambient conditions, especially when you add a mixed electrolyte to stabilize all these species like I was explaining. So as long as you add sulfuric acid, the efficiency dips by as much as 5% over a large temperature range. So, yes.
So how do you envision this being integrated into a city like Santa Barbara, for example? Would the city buy 2 or 3 of them, like water treatment plants, or would you have everybody have one in their, in their backyard, say, buried, or how would that work?
The way I would do it would be people have them in their backyards. They're pretty easy to tie into your house. I mean, it's just a DC battery. So anyone who knows how to hook up a lead acid battery bank into your system it would be the same technology. So yeah, I would see that. They scale better for larger, economically they scale better for larger installations, hence why there's really big ones and not a whole bunch of really small ones right now. But as the technology improves, it'll become more economical to make them smaller and smaller.
So kind of the same marketing model as the Tesla wall.
Yes, but a lot cheaper. So it would be a direct competitor with the Powerwall.
So the little one you have in the lab, how much power does that put out?
Not very much. Like
Like a microwave?
milliamps.
Toaster?
Like 20 milliamps.
Yeah, like so an LED, single LED.
Yeah, so for an LED, basically. Yes.
You said cheaper than a Powerwall. How much are Tesla Powerwalls today? I don't know.
It's $7,000 when you calculate the installation costs.
For how many kilowatt hours?
10 gigawatts.
Only 10?
Yeah. So that's pretty much a luxury item at this point. This would hopefully not be a luxury item. This would be something you would consider buying along with your PV system. So yeah, I would want to partner with solar companies that already have the infrastructure and the technicians to just be able to offer this as a solution to people who are already considering installing photovoltaic systems. And just say, hey, why don't you just add on a battery? That way you can use, you don't have to be tied into the grid, and then you can sell back during peak hours.
Would be okay in an earthquake in the underground?
Oh yeah. Yeah, it's just a big tank.
As long as your tanks are safe,
Yeah.
yeah.
Yes.
If you had a ideal membrane, is this something you could theoretically use for a car or for small electronics, or?
The problem isn't the membrane, the problem is the solubility. It's a solubility issue. So a thing to consider with that is that you could get rid of one side and use oxygen as your oxidant, and then you can run it in air, and using the V2 plus, V3 plus, you can get a lot more concentrated, you get a lot more power and energy density. So that might be something you may be able to use in a mobile application where you'd refuel your car with this stuff, and then you just run it through air, and you'd be able to get a lot of power out of it. The payoff would be higher energy density, so you make it smaller and less bulky.
But what would the cost be though? That's the gain, right? Is there a higher risk with the oxides or no?
You can't recharge it if you're running it in oxygen, so it's like you just have to like switch out the electrolyte every time you want to charge it. So yes,
When you charge the lead acid battery, you use gas,
yes,
oxygen, and hydrogen?
yes.
Would you say yes?
Not theoretically. So the voltages are minus 0.25 and 1 volts. Those are in between the 1.2 and minus 1.2 volts for oxygen evolution, hydrogen evolution. So as long as you stay within that range, you won't make hydrogen or oxygen. Any other questions? I see any in their hands. Yeah.
So the pumps, how do you power those with the system, or are they like?
So you need a little bit of power to get the pumps moving if you're going to charge it.
Them up to-
So you have to have at least a little bit of power going in order to cycle the system itself. So that's where the efficiency is dropped down from, is because you have to use pumps to move the electrolyte down through the system.
How much do you lose in efficiency?
I don't know. I haven't looked at that. Probably 10%.
What kind of pumps do you use?
Membrane pumps. So they just kind of flex the membrane back and forth to move liquid. Any other questions? Awesome. Well, thank you guys so much. Sorry, did I move out of the camera?
I was following you.
Cool.
Yeah. We'll bring up Henry in just a minute here, and Henry's going to talk about his home-built lathe that he's working on. So yeah, let's get him set up, and I don't know wherever is easiest. There you go. And then just put that somewhere in your real pile.
Okay, sounds good. This is the pointer?
Yep.
Excellent.
So give me just a minute.
Sure.
There's a very long delay, so.
No worries.
Yep, we should be all set.
Awesome. Hi, everybody. My name is Henry Biliniewicz, and I'm just a hobby machinist. We're going to take a journey to the other extreme of engineering and mechanics and chemistry, from the vanadium battery to working with steel. I'm a hobbyist. I'm not an engineer, and I found this great place, Santa Barbara Hackerspace, that has all machine tools to make other machine tools. So it's a great facility. They have a Haas, CNC center, a Bridgeport mill, a little I think is it a Logan or Atlas lathe that you take small cuts and you can make just about anything on it. So I'm here just to kind of go over the project that I'm working on, and then at the end kind of go over some theoretical stuff of, well, it's not really theory, it's epoxy granite machine base and lathes, and some recipes how to make your own machine base if you want to go down that path. But build it, yeah. If you want to build it, or you can buy it. Buy it, man, that thing is $20,000-$30,000 if you're into production. That's I think that is a Chevalier slant bed lathe with you know, fancy motor. Oops, man, I think I went too far, didn't I? Sorry about that. You got a preview. Anyway, I think I'll just stop right there. Come on. There we go. So this kind of machine is for high production, you know, production work, repeatability, quantity, precision. It has flat ways versus triangular waves, and it has a you know, changeable tool post on top. Big bucks, you know, and my thinking is, okay, why would I want to buy a Ferrari if I'm just going to go grocery shopping once a week, right? So this is my project. When you go from advanced to basics, and I just try to keep it as simple as possible. This is a 4x8 piece of tubular steel. It's hollow in the center. It's a 1/4 inch wall, and that's going to be my machine base. The ways are going to be attached to the top, and because it's hollow, I'm going to fill it with concrete, cap it at both ends, or cap one end, fill it with concrete, and give it some mass and some weight and some dampening properties, vibration dampening properties, by adding concrete. So there'll be very little flex, and so it'll be heavy, you know, on the magnitude of several hundred pounds, maybe 400 pounds all total. Here's a little bit close-up of the tube. The hollow tube will be spot welded, and again, the cavity will be filled with concrete to provide it mass, and then capped off. This is the current state of the drivetrain. I have a treadmill motor, DC. It's 130 volt DC at 3 horsepower peak. There's a, again, hopefully, where's the pointer on this thing? If I
that button right there.
Right there?
Yeah.
Cool, thank you. This is a bridge rectifier. So basically what I'm doing is taking 115, 120 volt AC, running it through the bridge rectifier, and then generating DC current. And again, the physics, you guys can probably tell me better why this happens, but I'm not exactly sure. But when you convert AC to DC with a bridge rectifier, it averages out only to 90 volts DC, and the motor can take 130. So I'm going to have to add a couple very large electrolyte, capacitors in there to kind of build up and store some of that energy and smooth out the waves. So hopefully I can get to 120 DC with some capacitors. And then here I have a controller with a knob, got it off of eBay, to speed up or speed down the motor. So my theory is I'm going to just control the speed of the spindle that I'm machining here with the motor and the controller, and just have one pulley, one-to-one V-belt pulley, driving the spindle on a 6-inch 3-jaw chuck. I'm in the process of cutting this down to fit the bearings. These are roller bearings, tapered roller bearings, which will fit inside a headstock. And again, the headstock is simple. It's going to be 1-inch thick steel, 12 by 12, or whatever I can get my hands on. At scrap yards, cut it down, and then cut the holes out, and then make supports for the bearings. You can run these things on oil and get a higher rotational speed. I think these things max out at about 3,000, 3,500 RPM. I mean, geez, I think the motor itself does 3,000 RPM. So I'm not going to run 3,000 RPM on this thing. It'll probably fly off and land in the backyard somewhere through the garage roof if I'm not careful. But and then I'll probably put some oil seals at both ends. So basically that's the drivetrain. I'm in the process of machining some pulleys out of aluminum. I'm going to put a 3/4 inch V-belt on it, and off she goes. This is a close-up of the motor. Like I said, 130 volt DC, 3.0 horsepower max. I think if you run it 130 volts DC, you would get 3.0 horsepower. Obviously, I can't generate more than 130. I'm just going to use 120 household current. And again, when you dial down the rotational speed, you're not going to get 3 horsepower max. You're going to get down maybe down to 1 or 1.5, whatever. But for what my intents and purposes, it's going to work. You know, like I said, I don't need a Ferrari. I just need something to get me to the grocery store and back. I need to machine some parts, some small parts at home. I love Santa Barbara Hackerspace. I live in Ventura, so I just can't come here every time I need to machine something. So I'm going to see if I can machine, make a tool to make machines at home. So let me back up. So here's a simple all-steel lathe that, again, you can make these things out of anything these days. Concrete, we'll get into epoxy, granite, or you can just make it out of all steel. And here's a simple design of steel plates drilled, held together with screws, lightly tack welded at different places. Again, it doesn't have to be super complicated and super difficult to make. It takes a lot of time and patience, but it can be done. And you can see kind of the U-shaped piece here, which is the support for where the ways are normally here. But most folks, they go ahead and spend an extra few bucks and they buy linear rails with blocks that run on those linear rails, and you'll always have very good precision using linear rails. But you can also go manual and get some hardened steel, scrape it, and that sort of thing. And it just depends what your budget is. And if you got a budget for linear rails, great. If you need to kind of hand screw, use the bridge mill to flatten it out to 1/1000th of an inch, it's there. So it's whatever your time and budget is. You can create these things out of chunky steel, and this particular design, it's angle iron. It's just 2 long of angle iron. You can get it in 1/2 inch thick cross sections. And what the gentleman has done, he's just cut a whole bunch of braces, and on the back side, he basically, let me see if I make sure I don't go too far. Basically, just cut pieces, U-shaped pieces, tack welded them to both angle irons, and then make cross bracing, and that's your lathe bed. That's where your rails are going to go, and there's enough structural rigidity there to support light machining. You don't have to have a cast iron bed. You can make it yourself. And if this flexes, gosh darn it, man, I'm holding this thing too fast. If this thing flexes, you basically can fill this with epoxy or some other, concrete. You fill up block the holes, and you can fill it with concrete and get some more mass that way. And again, here's a close-up of the construction. You can see the thick angle iron. It's 1/2 inch thick, and again, that's the bracing, just lightly tack welded, and that's your lathe bed. That's the guts of your machine right there. And again, here's the design. flattened, flat bed for the linear rails. This is the blocks that are going to ride on these rails, high wind. So this gentleman is making a very simple lathe with linear rails. These are pricey things, brand new. They're, a 4-block setup is $400 to $500, $600, depending on the size of the thickness of the rail. But you can get them used. Go for it. Sometimes you can find them really cheap on eBay. But that's the design. The carriage is going to ride on this rail with these blocks, and again, very simple design. And here's a rendering of what it's going to look like. So again, here's your cross bracing. Here's some plates, and it's another design, slightly, because this gentleman is using a flat bed. But this is the intent is to get your cross slide running on these bearing blocks, and you have repeatability and you have accuracy, because these things are like, I forget what there's no movement at all. It's like 5/10,000th of it, or 5/10,000th variance. It just doesn't move. Once you lock them in, they just roll continuously really well. So with that said, well, let's go into the theory of epoxy granite machine lathe bed. So you can build something really simple out of steel, or if you are thinking you can kind of make something out of a mold, yes, you can, because in the old days you have to melt and cast iron into a mold, and that's your machine base. Now with modern technology, techniques, you don't need that. And here's a comparison. Dang it. Keep doing this. Here's a comparison of dampening properties of epoxy granite compared to an aluminum machine base. And you can see one of the benefits of granite composite machine bases is it really absorbs vibrations in the machining process. So fewer vibrations or less vibrations, your part becomes cleaner and more precise, as opposed to your tools bouncing around and causing havoc in the machining process. So here's a gentleman who from YouTube. His name is Adam Bender, and he has a really good tutorial how to make an epoxy granite machine base. So he goes through his process, and I'm going to kind of touch upon what he does, and in comparison to the theory. Lathe bed fabrication. The ideal recipe of your mixture is a mixture of sand, gravel rocks, smooth gravel rocks on a quarter of an inch to no more than half an inch, and they have to be smooth riverbed gravel rocks. You want the rocks to kind of slide over each other, as opposed to jaggeding, the jagged edges catching on each other and causing voids. Some folks, and then Adam basically even skipped rocks altogether and just made a mixture of 80% sand, different size sand particles, with 20% by weight of epoxy. There's also, you can use, in this particular recipe, you can use 88% by weight granite aggregate, and the remaining mixture of percent by weight is your resin and hardener. And then here's the various sizes of particles, 1.5 to 2.25 millimeters by weight, and then other size particles and finer size particles. So this 88% of your total mixture is basically different sized sand particles to fill the voids, and create a really tight matrix when the machine base cures in the. So this is Adam's final sample. He came up with an 80 to 20% mix, and he threw in a little black dye to make it a little bit more aesthetically pleasing to the eye. It gave a really good surface finish. The voids are all gone. And now one thing I got to caution is when you make epoxy granite, you're going to blend all these materials together, and you're going to create air pockets in this thing. And the key is to get resin has a really long, they call pot life. It stays in the pot a really long time before it starts curing. They have resin now that's like 45-hour pot time before it starts hardening up. And what it is when you start mixing up the resins and the sands, you're going to get air bubbles. And the air bubbles need to be shaken and loosened up to the surface, so to avoid having very large voids in your matrix. So by shaking and vibrating the mixture, you're going to get all those air bubbles out to the surface, and they'll pop, and then thereby creating a very strong of machine for you. Otherwise, what you also can end up doing is putting in some steel reinforcements, some ribbing, that sort of thing, to give you additional weight and additional strength in your matrix. But if you make your matrix thick enough and deep enough and you vibrate it, it will be strong and heavy as for our intents and purposes. It'll be a very strong base. So first step of the process, you build a mold. You can build a mold out of, there's a product, melamine. It's a 4x8 sheet. You can get it for like $40 at Home Depot, Lowe's. You cut it into the size of your machine. You use some mold or release wax on the inside, or you can use, if you're going to do some more, high volume work, you make a mold out of aluminum plate. But this is Adam's mold for his machine base, which will be a base to do some measurements. So here's another, the sauce is the resin. You can buy clear from Amazon. It's like $70 for this SRC, and it's a 1 gallon kit, and by weight you probably need probably about 2 gallons worth roughly to make a substantial machine base. Again, remember, it's about anywhere from 12 to 20% by weight. The other 88% is for sand and aggregate. You want to try to use as little resin as possible, but it's the expensive bit. Rocks and sand are cheap. They're cheap, obviously. So the other type of resin is West Systems. Very expensive stuff. They use it to on boats. Exactly. It will last a long time, but it is pricey. It's about $189, $190 on Amazon. The other item that you're going to need. Here's another more reasonably priced epoxy. It's about 117, 118 bucks. This also works. It's called EpoxyCast 690. It's about a gallon, so a little bit more pricey than the SRC stuff that I said earlier on Amazon, but definitely a lot cheaper than the West System stuff. So again, there's epoxies out there, and this is pretty strong stuff too. So you need sand. You can get sand at Lowe's. This is what they call, I think, silver sand. Yeah, Comes in different sizes. I've seen it in 30 grit or 30 sieve size and then 20 sieve size. Again, the key is to get all the aggregates cleaned and washed, and so they fit into each other very nicely as a nice matrix. So very little voids are there so the resin has a chance to flow correctly and grasp all the various aggregates and get your machine base dried up nicely. Again, this is sample rocks. You can experiment. Rocks are cheap, again, but they do have voids, cavities. So you can see these rocks, again, jagged edges, they catch, and the sand should fill in all these voids. The best type of rock actually is this stuff right here. It's smooth, unpolished river pebbles that kind of been picked clean, by whatever and washed out. So they're really smooth, and you just flow with each other, and they flow onto each other. And then any gaps between the pebbles is filled with the sand aggregate, and that's your matrix. Another thing is you probably will want a shaker table, and again, the shaker table is used to keep the mixture vibrating, so it has a chance for the air bubbles to migrate to the surface. And you can make this out of a piece of plywood. I've seen actually what they've done is piece of plywood on top of a old rubber tire. It gives you that vibration, and people have strapped little sanders to their mold. So the orbital sander vibrates for a couple hours on top of a plywood board on top of a tire. And it's, again, very simple design. If you guys want to buy a $70 vibration motor and attach it to a piece of plywood with rubber feet, by all means. It's your budget. You make do with what you got. So this is the final end result of making a mold, mixing the aggregate sand, and again, in this particular case, there's no rocks involved. This was going to be a production piece for a customer, and you could see how smooth it was. So, and that's it. You can make a machine base out of epoxy, granite, steel. You're only limited by your imagination and your budget, which way you want to go with this. And you can make vertical machining centers, or you can make a lathe, and you can do anything you want. So, and I got to thank the Hackerspace folks, because without them, I still would be trying to do something out of my garage with hand tools. So, anyway, any questions? Yes.
So once you get the rails and the bed and all that, what do you have to buy commercially? Like you're stuck with a 3-dot chuck, for example, and tail pieces and all that, or can you improvise that sort of thing also?
3-jaw chuck, yes, but it's probably cheaper. You can buy them on eBay for 150, 200 bucks. You need a backing plate to attach the 3-jaw chuck to, and then that backing plate attaches to spindle. So in my particular case, I'm going to, machine some threads on the spindle to go into the backing plate. You can try to make, you probably could weld a backing plate to your spindle and balance it out and machine it as one piece, and then you just attach your 3-jaw chuck directly to the complete spindle assembly with screws, and then you have to kind of fine tune it and balance it out. So, but so any other questions? Well, thank you.
So your lathe, you would do for the rails. I don't think you went into too much detail.
Okay, I'm still debating whether I'm going to try to make my own rails and harden steel and scrape it, or if I can find a good deal on some linear rails, I'll go with that. I'm leaning towards getting some hardened steel and just scraping it, or having it just put it on a Bridgeport and smooth, get a really good surface on the top and then on the sides. And I know your Bridgeport is pretty accurate. I think it's like good to 1/1000th of an inch over like 36 inches, and I can live with that. That's some pretty good tolerances. If I can start out at 0 and just end up at 1/1000th variance at 36 inches, I think we're okay. So yes.
So for that epoxy granite stuff that you're talking about, how machinable is that once it's cast and dried? Is it easier to mold it with holes in it, or can you drill holes in it afterwards?
You can, but the base should include your inserts. So if you're going to drill, if you're going to screw stuff into the base, you should actually mold.
Just cast those into it?
Cast those into it, yes, yes, absolutely. That's the best way of
So
doing
the
it.
video had a steel frame that the rails would end up bolting down to.
Right.
So that was all cast into the epoxy granite.
Yes, yes, yes.
Do you think you're gonna add, I guess you call it screw feed so you can cut threads or not?
Yes, ultimately what I'd like to do is to add some stepper motors to be and a screw lead to actually have it controlled by like an Arduino.
So not physically attached to your motor, it would be a separate drive then.
Yeah, exactly. Yeah, once I crank up the speed on the motor to to whatever the ideal speed is for the operation, then theoretically the stepper motors with the Arduino will move the tools back and forth as necessary to the desired shape. And again, I'm not trying to make a CNC machine out of this. I just want something that I can know that it will run first manually, and then as my budget increases, I'm going to add some stepper motors to it. So, and a little bit of Arduino. Yes.
So are you going to have one tool, or are you going to come in from the side as well?
Yeah, there'll be X-axis and Z-axis. So again, the cross slide will move on the X, and then also will move on the Z-axis for diameter cutting as necessary. And if you get stepper motors controlling an Arduino or some sort of control unit, it actually you can program these things these days to actually cut threads that it's smart enough to move at various points and depth that it will run through a sequence and actually cut threads for you if that's what you want it to do. So, yes.
If you're using linear rails for the base, are you going to have the tailstock mount to the linear rails, or does that come out?
Actually, yes, you could probably have your tailstock riding on the linear rails also.
If you were going with linear rails, is that what you would do, or would you?
I would probably do it that way because you have two parallel points of attachment, both for the cross slide, and you can use that as a also for the tailstock. Absolutely, as long as the rails are beefy enough. The thicker the rails are, the more pricier it is. I think on say like on a 4-foot lathe, you want to machine some really heavy stuff, you probably need to get 30 to 35 millimeter rails. And well, 25 might cause a little flex, but yeah, those things get pricey, brand new. The Hiwin, HIWIN, linear rails, they get pricey. Again, if you can find some cheap Chinese knockoffs and you're willing to live with not exact precision, then go for it. I mean, like I said, if I can get a deal on linear rails, I'll put it in. Okay, we'll talk. So, any other questions?
So, what's your goal for your home machine? Any particular projects?
Yeah. I want to I want to build my own sidecar. I ride motorcycles and I have a sidecar. I saw a really cool design from Europe that I want to build. Another thing I would like to build is, again, don't laugh at me, guys, is a pedal-powered pontoon boat. I've seen you can buy these pontoons and from China for about $100, and you blow them up, and you can make a recombinant bike, water bike out of, if you if you can machine some stuff, and you can sit in it and pedal. And I want to just take that out possibly next summer in the harbor. I don't want to do any paddle boarding. I just want to be able to sit and pedal and get the little propeller to spin and take me around the harbor. So that's the other thing I want to build. And without machine tools, it's hard to kind of, cobble things together with a hacksaw and crazy glue. So you kind of have to go through that next step. And to build certain things, you need some machine tools. And once I get this done, then I can work on other projects. But yeah, so that's me, hobby machinist. I'll cut off real quick, but I push paper for a living. I'm a supply chain manager. I do buying and ordering of parts. All right, so this is the way I kind of keep sane in the evenings, is kind of blow off all that business stress, and I come and play in machine tools and build stuff. Kind of keeps me balanced and grounded. So again, that's my story. I'm sticking to it. And thank you, everybody, if you have any questions. So, thank you, guys. And I apologize for the technical mix-up about the fast forwarding, but stuff happens. No, it's Velrex. Velrex fiberglass sidecar, and I have it attached to a Honda CB750. So I always get thumbs up. The kids